Now next topic, that is dynamics of rotational motion about a fixed axis. Now suppose here the particle P1, okay, here this one is the particle P1 for which the position vector with respect to the origin of Cartesian coordinate system, that is R1, that is executing circular motion under the effect of force F1 acting on it, and it is executing circular motion with radius R1 in XY plane. So we can say here the fixed rotational axis, that is the Z axis. We consider here the fixed rotational axis, that is Z axis. Now here when force F1 that is acting on particle P1, which is displaced from P1 to P1 dash in suppose time interval delta t. So it is executing the circular motion on the circular path having radius equal to R1 with the center on the axis here at the origin. Okay. Now here the displacement of this particular particle from P1 to P1 dash, that is ds1, okay, and this displacement that is taken infinitesimal small, which one is subtending angle d theta at the center. Okay, so here we can give in this time interval delta t, when particle is displaced from P1 to P1 dash, means that is equal to ds1, the work done under the effect of force F1, that is dw1 equal to F1 dot ds1. Okay. Now as per definition we give this one is the work done. So here suppose the angle between ds1 and F1, that is phi 1. So we can write F1 ds1 cos phi 1, that is the work done under the effect of this force F1 by particle P1. Clear? Now see here, this displacement vector and this radial vector, if we extend this one like this, then both will be perpendicular to each other. So this angle, that is 90. Now suppose here the angle between force and this position vector, that is alpha 1, then from figure we can write phi 1, that is this 90 minus alpha 1. Okay, so we can write here F1 ds1 into cos 90 minus alpha 1, so that is cos 90 minus alpha 1, that is sin alpha 1. Now ds1 and arc, that is angle into radius, so r1 d theta. So we can write here this is equal to F1 r1 sin alpha 1 into d theta. But see here, as per definition we can say F1 r1 sin alpha 1, that is the torque acting on particle under the effect of force F1. So we can write dw1, that is tau 1 into d theta. Now if more than one forces are acting on the body, then in that particular case we can write the equation of the total work done, that is tau 1 plus tau 2 plus tau theta up to tau n into d theta. The summation of the torque will give you the resultant torque acting on the body. So we can write dw, that is tau d theta. And now see, this equation is exactly like dw equal to f ds. Okay. So here we can say this thing, this expression give the total work done by the external torque when the body is rotating about a fixed axis. Now, say here, now we have dw, that is equal to tau d theta. Divide that equation on both the side by dt. So dw by dt, the rate of doing work, that is called power. So power P, that is equal to tau d theta by dt. D theta by dt, that is angular speed omega. So we can write power P, that is equal to tau into omega. This equation is exactly like the equation of the power in the translational motion, power P, that is F into V, right? Now, we can say here, in a perfectly rigid body, there is no internal motion. So the work done by the external torque increases the kinetic energy of the body. Okay. So W, that is equal to half I omega square, and that is equal to tau into theta. Now differentiate this equation both the side with respect to time t. So d by dt of W, d by dt of I, half I omega square equal to d by dt of tau theta. Now here half I is constant for the given fixed rotational axis. So half I, differentiation of omega square, that is 2 omega, and of omega itself, that is d omega by dt, equal to tau d theta by dt. Here 2 cancel. D omega by dt, that is alpha. So on left hand side we can write I omega alpha. On right hand side tau d theta by dt, that is omega. This omega is cancelled. So we can write torque tau, that is equal to I alpha. This equation is exactly like the equation F equal to ma in translational motion. So by discussing this analogy between the equations of rotational motion with constant acceleration and the translational motion with constant linear acceleration, we can understand this thing, the role of respective physical quantities, that is the same one in respective motions. It implies that, see, the role of force in translational motion and the role of torque in rotational motion, that is identical one. Here A represents the linear acceleration. Here alpha represents the rotational, means angular acceleration. Here in translational motion, mass represents the inertia of the body. Exactly like that, in rotational motion, moment of inertia represent the inertia of the body. So in this way, easily you can understand the role of respective physical quantities in their respective motions. Clear to all of you? Here we can say this thing, just as force produces the acceleration, torque produces the angular acceleration in the body, and angular acceleration directly proportional to the torque applied as well as inversely proportional to the moment of inertia. exactly like here, linear acceleration, right? So we can say this thing, this equation number 3, that is called Newton's second law for the rotational motion about a fixed axis. Clear?